Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1950 witnessed a significant advancement in the understanding of fundamental particles, an achievement largely attributable to Cecil Frank Powell's work, specifically his paper Mesons produced by cosmic radiation. This research, a culmination of earlier efforts and a pivotal contribution to particle physics, provided compelling evidence for the existence and properties of mesons, transient particles possessing a mass intermediate between the electron and the proton. To fully grasp the import of Powell's publication, one must first consider the scientific landscape from which it emerged. The early to mid-20th century marked a period of intense exploration into the structure of matter. The discovery of the electron and the proton established the basic building blocks of atoms, while the development of quantum mechanics provided the theoretical framework for understanding their behavior. However, certain experimental observations defied complete explanation within this framework. Cosmic rays, high-energy particles originating from outer space, bombarded the Earth's atmosphere, producing a cascade of secondary particles. These showers of particles were a puzzle for physicists during this period. In 1935, Hideki Yukawa proposed the existence of a particle to mediate the strong nuclear force which binds protons and neutrons within the atomic nucleus. This particle, later termed the meson, would have a mass somewhere between those of the electron and the proton. Yukawa's theory provided a crucial theoretical impetus. However, direct experimental verification proved elusive. The search for Yukawa's meson constituted a central scientific challenge. Early attempts to identify this hypothetical particle relied heavily on cloud chambers, devices that allowed the visualization of particle tracks. However, the relatively low resolution and the limited sensitivity of cloud chambers hindered progress. Another method employed was the photographic emulsion technique, the method to which Powell would ultimately make his significant contribution. This technique utilized specialized photographic emulsions, plates coated with silver halide crystals, to record the passage of charged particles. When a charged particle traverses the emulsion, it ionizes the silver halide crystals, creating a latent image that can be developed and observed under a microscope. The advantages of the photographic emulsion technique, particularly its high resolution and its suitability for prolonged exposure to cosmic radiation, made it an ideal tool for the search for new particles. Earlier attempts, using photographic emulsions, had produced some limited results, but the techniques needed improvement. Powell, a physicist at the University of Bristol, possessed a deep understanding of photographic emulsion technology. He refined the techniques of emulsion processing and developed methods for analyzing the tracks of charged particles. Powell's specific contribution involved the use of extrasensitive photographic emulsions, developed in his laboratory, exposed to cosmic rays at high altitudes. These emulsions, when examined microscopically, revealed the tracks of particles with previously unseen characteristics. His team, including Giuseppe Chiellini, Cesar Lattes, and Hugh Muirhead, identified tracks that could only be explained by the production and decay of a new particle. This particle was the Pion, the first meson described by Yukawa. The work involved careful measurement of the range and ionization of the particle tracks, allowing for the determination of the particle's mass which agreed with the predictions of Yukawa's theory. This represented a significant moment for the field. Powell's 1950 paper, a comprehensive account of these findings, presented robust evidence for the existence and properties of the Pion or pi meson. The paper detailed the experimental setup, the processing methods, and the analysis techniques used to identify and characterize the particle tracks. Presented within the paper were detailed measurements of the Pion's mass, charge, and lifetime. Furthermore, the paper provided observations of the Pion's decay, which resulted in the production of another particle, the muon, and a neutrino. This chain of events provided solid evidence that the Pion played a crucial role in the decay. The publication included high-resolution photographs of the tracks of the Pions and their decay products. The photographs served as potent visual evidence, confirming the existence of this new particle. The meticulous attention to detail, combined with the compelling visual evidence, made a powerful case for the scientific community. The immediate impact of Powell's work was profound. This paper provided definitive confirmation of Yukawa's theoretical prediction of the meson. The successful identification of this particle brought a new era of particle physics. The discovery of the Pion opened new avenues of research into nuclear forces and the fundamental constituents of matter. It offered a critical step in the development of the standard model of particle physics, the theoretical framework that describes the fundamental particles and their interactions. Moreover, Powell's work demonstrated the effectiveness of the photographic emulsion technique as a tool for particle detection. This promoted the general use of this method. Powell's findings directly influenced subsequent research. The photographic emulsion technique, refined and improved, became a standard tool for particle physicists. The discovery of the Pion led to a surge of interest in the study of mesons and other subatomic particles. Physicists soon learned that the Pion was the lightest of a family of mesons which participate in a wide range of nuclear processes. The identification of the Pion also spurred the development of particle accelerators, devices designed to produce high-energy particles. Particle accelerators allowed physicists to study these particles in controlled environments, leading to the discovery of a vast array of new particles and a greater understanding of the forces involved and around. The original publication received widespread acclaim. The scientific community widely accepted the identification of the Pion as groundbreaking research and recognized its importance. Powell's work earned him the Nobel Prize in Physics in 1950. Recognition of his significant contributions to the field. The award served as a testament to the significance of his research. The precision and the thoroughness of Powell's work set a high standard for experimental physics. The paper remains a classic example of experimental rigor and scientific clarity. The techniques and methods developed in this work influenced later research. Several individuals and prior works profoundly influenced Powell's research. Yukawa's theoretical predictions provided essential insight. Powell's prior work in photographic emulsion techniques, developed during his early career, enabled the success of his experiments. The pioneering research of Patrick Blackett and Giuseppe Occhialini, who had used cloud chambers to study cosmic rays, brought the experimental tools as well. Powell's colleagues, notably Occhialini, Lutz, and Muirhead, played vital roles in the experimental work and the analysis of the particle tracks. The collaboration was an important factor in the success. The collective effort helped to refine the experimental methods, identify the relevant particle tracks, and interpret the data correctly. The influence of the work on the work of others extended beyond the direct application of his methods. The discovery of the Pion had a profound effect on the field of particle physics. The techniques that Powell developed were used to study other particles, contributing to the body of knowledge regarding the subatomic world. The work of Richard Feynman, Murray Gell-Mann, and others in developing the Standard Model was influenced. The Standard Model provides a comprehensive description of the fundamental particles and their interactions. Powell's contribution in providing a first experimental proof of the Yukawa's meson gave a foundation for the Standard Model of particle physics. The work on the Pion aided the development of gauge theories, which describe the forces of nature. The work also has significant impact in condensed matter physics. The development of particle detectors, such as the silicon strip detector, benefited from the techniques used in Powell's work. The 1950 paper by Cecil Frank Powell stands as a landmark achievement in the history of particle physics. It provided the first definitive evidence for the existence of the Pion, a crucial particle predicted by Yukawa's theory. Powell's work, rooted in earlier research and supported by significant experimental innovation, demonstrated the power of the photographic emulsion technique. The legacy of this research continues to impact our understanding of the universe's fundamental nature. The precision of his methods set a new standard, and his contributions continue to provide insight into the world around us.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.